So hi everyone, in this short video I'm going to remind us all of the basic definitions and results about separable extensions. Right, so we start with the definition of separability of a polynomial. So say you have a polynomial f over some field k. So this polynomial is said to be separable if it has no multiple roots in some algebraic closure that you fix. And note that potentially this could have been a definition that depends on the choice of the shouldn't, but of the choice of the algebraic closure, or maybe of some algebraic extension that you care about, but actually it isn't. So separability actually can be checked within K, and you don't have to do anything outside of the arithmetics of K in order to determine separability and therefore defining it. And indeed, you can show that F is separable if and only if the GCD and F and F prime is 1, if they are co-prime as elements in the ring. In other words, if this ideal is everything, right? It's the entire polynomial ring. So let's prove that just to remind ourselves of these things. So we have two directions. So initially, I'm going to assume that F is not separable and prove that this is not one. So if F is not separable, then it has a double root in the algebraic closure. So let's denote it by alpha. So in the algebraic closure, over the algebraic closure, we can factor f of x as x minus alpha squared times g of x. Well, g can be also vanish at alpha, but at least we have this factor. And again, everything happens now in the algebraic closure. Okay, so the derivative of f prime, right. So what I'm trying to prove is that you don't have to worry about the algebraic closure, but the proof goes through the algebraic closure. Now, the derivative of f prime, just by usual derivative rules, is x minus alpha squared g prime of x plus 2x minus alpha g of x. So you see that both f and f prime are in the ideal that's generated by x minus alpha. Right? Both of them are divisible by x minus alpha. In what ring? In the ring of polynomials over k bar. So in that particular polynomial, they don't generate the entire ring. And this actually also implies that they don't generate everything in k of x. Even though everything we did is in k bar, the idea generated by them, the fact that it does generate anything here also implies it does generate anything here. That's an exercise. Okay, so that's a proof sketch. Now in the other direction, so I'm assuming, so now it's a contrapositive of the other side. So what we want to show is that there exists some alpha in k bar such that both f and f prime vanishes out. Namely, I want to, so saying that f has a double root is what I'm saying is the equivalent of saying, it's actually almost the definition of saying that f and f prime vanishes at that potential root. And indeed that's kind of obvious. So let's just see that. So if I'm showing that, then first of all we know that f of alpha is 0. And so because of that, we know that f of x has a factor of x minus alpha. Now, if I compute the derivative of this, then I get g of x, because the derivative of this is 1, plus x minus alpha g prime. And since f prime of alpha is 0, so this is 0 when you substitute alpha, you get the g of alpha is 0, because this is 0. And so going back here, you see that f has like x minus alpha appears twice in the expansions, because g also contributes x minus alpha. So you can write f as x minus alpha squared times another polynomial h of x. So really, if we want to show non-separability, it suffices to prove that both f and its derivative vanishes at the point. So let's see why this is true. Assuming that, right? Assuming that this doesn't hold, I'm showing that this doesn't hold. So assuming that f and f prime don't generate the entire polynomial ring in k of x, then because k of x is a PID, they generate some ideal that is principal, and let G be that element or an element that is the unique generator for this ideal. And we know that the degree of G is larger than 1, because if it was a constant, then this would have generated the entire polynomial ring. Okay, so because f is contained in this ideal in particular, we have that f is some constant, f F is A times G, sorry, and F prime is B times G. Right. And now what I'm saying is that any root of G in an algebraic closure, right, any alpha which is a root of G in an algebraic closure, and it has a root because the degree is at least 1, is a common root both to F and to F prime, which is what we wanted to show. Good. So far we talked about polynomials being separable. Now we're going to talk about elements being separable. So say you have an algebraic field extension. We only consider algebraic field extension, even though you can do it more generally, because this is an element by element definition. So an element alpha in L, in the big field, is separable over K. Of course, you have to say the over K because that's where the polynomial, the irreducible polynomials are coming from. If there exists a separable polynomial in K, which vanishes at alpha. Right, so an element is separable if there is a polynomial over K that vanishes at alpha. And equivalently, you can just require that from the minimal polynomial of alpha over K. Because if there is such a polynomial, that would be that polynomial. Good. So an extension is called separable if every element, as we define now, is separable over K. Every element in L is separable over K. Now, separable extensions actually are kind of typical. So for example, which is the typical example when you do Galois theory, but it's actually not the setting that we have in the course. If the characteristic is 0 of the ground field, of the lower field, then any extension is always separable. So to see that, just as an example, even though again we will never consider such fields in our course, take any element in L and consider its minimal polynomial. And of course, I can assume the degree is at least 2, because if it is 1, then it's just in the field, and the polynomial is separable because it has one root anyhow. So assume that the degree is at least 2. And so because the characteristic is 0, we know that the degree of the derivative is 1 lower than the degree of the polynomial, right? I'm assuming the degree is at least 2. That's how usually derivatives work, right? They reduce the degree by 1, unless the characteristic is positive, in which case weird things can happen. And so in particular, of course, the degree of F prime is larger or equal than 1, and it's strictly smaller than the degree of F. Right. So now let's continue using our previous claim. So assume by contradiction that F and F prime don't generate anything, they generate just G, right? I'm using the claim that we just proved. In order to argue about separability, I'm going to compute the kind of GCD of F and F prime. Or just show you the upper prime. Same thing. So let's assume by contradiction that F and F prime actually don't generate the entire ring. Namely, G is not a constant, it has degree at least 1. So this means that G divides F, because F is in this ideal, but F is irreducible. So the only way that can happen is that G equals F. Right? But then, by the same reason, we know that G divides F prime, and that doesn't add up with the degrees, right? Because G is F, and F cannot divide F prime, because F prime has a lower degree than that of F, and it's at least 1, not a 0 polynomial. Okay. Now, in characteristic P, larger than 0, it's not that all extensions are separable. In fact, if you consider finite extensions of finite fields, these are always separable. And that's why also in Galois you don't see much of separability even when you do consider a positive characteristic, because usually in positive characteristic what you do is work with finite fields and extend them, look at finite extensions of them. So why is this true? It's kind of the same proof, but for different reasons. So consider a field extension L over K, which is a finite extension, and K is a finite field of characteristic P. Then, so we know, because we understand finite fields, we know that the elements of L are all roots of this polynomial, right? If L is of, for some n, P to the n is the size of L, or n is the degree extension, no, p to the n is the set of L. So we know that we have, we know that all roots of L, all elements of L are roots of this polynomial. This is something that you prove. This is one way of defining or understanding finite field as the splitting field of this polynomial. And when you look at this polynomial and just compute its derivative, you see it's -1 because this contributes 0. The p to the n, because n is at least 1, vanishes as a coefficient, so you get only -1. In particular, f and f prime have are coprime. And so f is separable, implying that all elements in L, because the roots of that polynomial are separable. Good. Now, if you want to find examples of non-separable extensions, you actually do have to work a bit hard or harder. So here is the canonical example. So you take some field of characteristic P, I call it little k, and now you consider two extensions. So maybe this is little k, just some field of characteristic P. And then you consider, I mean, you know that you have to consider infinite fields of characteristic P. So one thing you do is you consider adjoining k some t to the p, and L is going to be k to the t. More precisely, I'm going to take some element, I'm going to consider this, I'm going to start with L actually. I'm going to consider the rational function fields in T over K, and then capital K is adjoining not T, but T to the P. Right? These are, so this is a field extension of that, and that's a field extension of that, and yeah, good. And these are infinite fields of characteristic P. Right, so now you can ask yourself, what is the minimal polynomial of T as an element in L over capital K? So that would be x to the P minus T to the P. We need to show that technically, but that's the minimal polynomial, right? T to the P is an element here. You can use it as a coefficient. It turns out that this is irreducible. Oh yeah, good. So this is the irreducible polynomial of L of T over K. But if you look at it for a second and you look how it looks in L, then it actually factors at x minus T to the P. Right, that's because all of the binomial coefficients have a p in the upper part and no p in the lower part. So all of the, if you open it according to the binomial coefficients, then all of them vanish except for the extreme two. Good. So you see this is an extension which is not separable because, in fact, something even more extreme happened. You found an element here that its irreducible polynomial doesn't just have a multiple root. Actually, it has only one root multiple p times. So it's going to be extreme. This is an extreme example. But actually, it's not an extreme example. That's essentially what you can always make sure to make set to happen. Indeed, so let's have the right definition and the theorem that concerns that. So let's say that over K is a field extension. Again, the characteristic should be positive because otherwise separability is given. We say that L over K, the extension is purely inseparable if every element in the top field is the root of a polynomial of this form. Which, by the way, means that, I mean, it requires a proof. It means that the irreducible polynomial of alpha has only alpha as its root. Okay. So that's the extreme then from being separable, in which case all the roots are distinct. And the theorem that we are going to use again and again, and some variant of that, and I'm going to talk more about it because it's not, I mean, it is known, but I don't think you see every Galois theory course that you are given. It's kind of depending how much separability is interesting by the lecturer. So let's say that you have, again, an algebraic extension over K. Then first of all, and that is usually taught, the set of all elements in L that are separable over K form a ring, form a field, which is kind of surprising. I mean, if you take two A and B's and which are separable, each of them has its own irreducible polynomial, and there are no repeated roots in those particular polynomials. But you know how you can infer from that the irreducible polynomial of their sum, product, and so forth also has repeated roots. But you actually don't show it like that. You use it's similar to what happens when you want to show elements are algebraic. I mean, algebraic elements form a field. Right? Why is it the case that if A is algebraic and B is algebraic, and also A plus B is algebraic? Right? Why, the fact that A has a polynomial over your ground field that makes it vanish, and also B, it doesn't mean we know how to cook up easily a polynomial that such that A plus B vanishes up. So it's kind of the same thing. You do it by dimension considerations, and we'll talk about it. Like there you have the notion of a degree of an extension. Turns out that you can break the degree to the separable degree and the inseparable degree, and that's essentially what's happening here. But that's true. Like separable elements are closed under additional multiplication. So if you have field L over K, then you can always do K sep, which is considered the subfield, as it turns out, of L that consists of all separable elements over K. So this is a separable extension. And it turns out that the remaining part is a purely inseparable extension. So that's what's written here. Right, so when you do Galois, for example, you want to be separable. So when you do Galois, usually you're here. And then this part is kind of trivial when you do Galois, because it turns out that any automorphism can be extended uniquely from that level to that level. So when we will do Galois theory in the context of our course, we will break, sometimes when needed, we will break a general extension to its separable and purely inseparable, and do the Galois here and infer back to it. We should also say that there is another way of doing that, which we'll also use, in which you have K here, and then you actually do it kind of in the reversed way. At the bottom level, you put a purely inseparable field extension, and above it, you set up a separable extension. We will need that as well. But as I said, this is not something that you usually see in Galois, so that's not part of so I'm not putting it in these videos, which are mostly about a recap of Galois theory. So the next video is going to be about Galois extensions, and we are going to kind of sketch the proof of the main result of Galois theory, the correspondence between subgroups and subfields and so on.